So, definition of an extrema, so that's a max or min, and this can be an absolute max, absolute minimum, or relative max or relative min. So basically, f of c is the minimum of f on the interval I when f of c is less than or equal to f of x for all x in the interval. It's the lowest y value in that interval. Maximum, it's the biggest y value in that interval. The min and max of a function on an interval are the extreme values, or extrema, of the function on the interval. The min and max of a function on an interval are also called the absolute min and absolute max, or the global minimum or global maximum on the interval. Extrema can occur at interior points or endpoints of an interval. Extrema that occur at the endpoints are called endpoint extrema. Now, the extreme value theorem, if f is continuous on a closed interval, a to b, then f has both a minimum and a maximum on the interval. Finding min and max values, the extreme value theorem, like the intermediate value theorem, is an existence theorem because it tells of the existence of min and max values, but does not show how to find these values. Use the min and max features of a graphing utility to find the min and max on the following two that you see, just to play with it. Here we're going to find it, find the value of the derivative at each relative extremum shown. So f of x equals 9 times x squared minus 3 over x cubed at 3, 2. So f prime, it's a quotient. So 9 times 2x times x cubed minus 9 times x squared minus 3 times 3x squared all over x to the third squared. Simplifying, that gets us 18x to the fourth minus, in brackets there, we've got 27x to the fourth minus 81x squared over x to the sixth. Could have probably done this a little easier, but I'm just going with this. Practicing quotient rule here. And then that simplifies to negative 9x to the fourth plus 81x squared all over x to the sixth. I could pull out a negative 9x squared. And then that kind of simplifies to negative 9 times x squared minus 9 over x to the fourth. Plug in 3. Gets us 9 minus 9 on top and 81 on the bottom, and that's going to get us just 0. At 3, 2, it's got a slope of 0. For b, f of x equals absolute value of x at 0, 0. Well, the limit as x approaches 0 from the left is negative 1, and the limit as x approaches 0 from the right is positive 1. Derivative doesn't exist at f of 0 because the limit from the left and the right don't agree. They're not the same. Part C, find the derivative of sine of x. F prime of x equals cosine of x, and then we want to find it at the 2 points. So cosine of x at pi over 2 is 0. Cosine of 3 pi over 2 is also 0. Interesting. Those kind of look like relative mins and maxes, just like they were on part A. Definition of a relative extrema. If there's an open interval containing c on which f of c is a maximum, then f of c is called the relative maximum of f. Or you can say that f has a relative maximum at the point c, f of c. And relative minimum for the same thing at the point c, f of c. Relative max and relative min are sometimes called local max or local min, respectively. Definition of a critical number, let f be defined at c. If f prime of c equals 0, if the derivative at that x value is 0, it's a critical number. C is a critical number. Or if f is not differentiable at c, then c is a critical number of f. So we take a look at the left. F prime of c doesn't exist at c here, and so that's a critical number. And here, f prime of c equals 0, horizontal tangent, that's also a critical number. On the AP exam, critical numbers are sometimes referred to as critical values. Relative extrema occur only at critical numbers. If f has a relative minimum or relative maximum at x equals c, then c is a critical number of f. That means if you take the derivative and find out where it equals 0, you found your critical numbers. And you found your relative max or min. And you can take a look at that using f of x equals e to the x, natural log of x, sine of x, tangent of x to kind of see which ones have critical numbers. Only one of the functions down there has a critical number. Guidelines for finding extrema on a closed interval. To find the extrema of a continuous function f on a closed interval a to b, first find the critical numbers of f in a to b. Evaluate f at each critical number in that open interval a to b. Then evaluate it at the endpoints. And the least of these values is the minimum, the greatest is the maximum. What does that look like in practice? Well, get to that. When an AP exam question asks for an absolute extremum of a function on a closed interval, be sure to evaluate the function at the endpoints of that interval. For help on the algebra in example 2, you can see example 1a in chapter 3, algebra review on page A40. Okay, example 2, we're going to find the extrema of the following functions. So I first need the derivative of a, which is going to be 12x cubed minus 12x squared. And I can factor that pull out a 12x squared, so that's 12x squared times x minus 1. Means our critical values are 0 and 1. Now I need to take those two numbers, plug them into the function. So f of 0 is 0, f of 1 is negative 1. And then check the endpoints. So f of negative 1 is 7, f of 2 is 16. Okay, and out of those, the minimum y value is negative 1. So the minimum is that f of 1 equals negative 1, and the max is going to be at f of 2, 16. B, same thing, come up with the derivative. So that's going to be 2 minus 3 times 2/3 times x to the negative 1/3. That simplifies to 2 minus 2x to the negative 1/3. Critical values are going to be at 0 and 1. How do I know that? Well, I'll probably need to get some more information up here. Here we go. I'm kind of doing it in backwards order, and I'm not going to fix it. So 2 minus 2x to the negative 1/3 that we've got going on here can be simplified to 2 minus 2 over x to the 1/3. Get that to be one fraction, so I take the 2 top and bottom times x to the 1/3. What makes that 0? Well, I can't plug in 0, so that's a critical value. And then if I plug in 1, that makes the numerator 0. That's the other critical value. That's how I got 0 to 1. Plug in 0 to the original function, we get 0. Plug in 1, we get negative 1. Plug in the endpoints, f of negative 1 is negative 5. F of 3 is about negative 0.24. I kind of rounded there. Our minimum in that closed interval is at negative 1, negative 5. Our maximum is f of 0 at 0. Okay, find the extreme of the following functions on the indicated intervals, continuing that. So I need to take the derivative of our function. And so that's just f prime of x is 2 cosine of x minus, and then derivative of cosine 2x is negative sine of 2x times 2. Chain rule there. That simplifies to 2 cosine x plus 2 sine of 2x. I can pull a 2 out of both of those. But then sine of 2x, that's a double angle, so that's 2 sine x cosine x. Now I can pull a cosine of x out of both of those terms. I've got a product. I want to see where that equals 0, so I take each factor and set it equal to 0. So 2 cosine of x equals 0. Divide both sides by 2. So where does the cosine of x equal 0 in the unit circle? That's at pi over 2 and 3 pi over 2. Where does 1 plus 2 sine x equal 0? Well, that's the same as saying where does sine of x equal negative 1/2? Well, for that I can use the unit circle. I'm looking for a y value of negative 1/2. There's 2 of them, both one in the 3rd quadrant, one in the 4th quadrant. And that's at 7 pi over 6 and 11 pi over 6. And then, so those are our critical numbers. I put them in order from smallest to largest, so pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. Now I need to plug them into the original function as well as the endpoints to see where our min and maxes are. F of 0 is negative 1. F of pi over 2 is 3. F of 7 pi over 6 is negative 1.5. F of 3 pi over 2 is negative 1. F of 11 pi over 6 is negative 1.5. And F of 2 pi is negative 1. I look at those. I've got two minimums at negative 1.5. So F of 7 pi over 6 and F of 11 pi over 6 are my two minimums, relative minimums. And then our maximum is at pi over 2. So f of pi over 2 equals 3. And now you try it on your own.